Welcome everyone. It's my pleasure to introduce Professor Michael Shaver of the School of Natural Sciences at the University of Manchester. Michael is here today to present his talk on sustainable and functional polymers. There is a lot of discussion around single-use plastics at the moment, with the focus being on how detrimental they can be for the environment. In reality, this is a much more complex problem, which Michael can elaborate on in the talk. Michael is a professor of polymer science at the University of Manchester, where he leads initiatives in sustainable polymers, plastics and materials for the Henry Royce Institute. Within the Royce, he is the director of the new Sustainable Materials Innovation Hub, which supports small and medium enterprises in Greater Manchester to make smart, sustainable material choices. After studying for a PhD in his native Canada from the University of British Columbia and an NSERC postdoctoral fellowship at Imperial College London, he began his independent research career at the University of Prince Edward Island before working at the University of Edinburgh from 2012 until leaving for Manchester in 2019. Michael has been recognised with a Macro Group Young Polymer Scientist Award, 2 Canada Foundation for Innovation Leadership Awards, and fellowships in the Young Academy of Scotland, the Royal Society of Chemistry, and the Institute of Materials, Minerals and Mining. His research is focused on the development of biodegradable materials as a complement to petroleum-derived plastics, accessing renewable, degradable and non-toxic materials. The applications for this work range from biomedical materials, water purification and composites, all centered on the development of sustainable and functional polymers. Over to you, Mike.
Cool, thanks very much. First of all, thanks for the chance to kind of talk to you today about some of the stuff that we do. Hopefully you guys can now see slides. I did sort of talk about this stuff and use this as an entry slide before 2020, but holy crap, 2020 sucks. It does sometimes feel like the end of the world. And whereas last year, 2019 for me was like, oh, the end of the world is about plastics and sustainability. There's lots of reasons this is now the end of the world, from racial injustice to massive global pandemic to this continued issue with the end of the world and our environmental influence over it. So instead of being all glum on a Wednesday, I figured it was useful to sort of at least use this as a starting point for how we might be able to change things. So really trying to say, okay, well, what can we do from a polymer chemistry perspective, using chemistry, engineering, social science, economics, in a very interdisciplinary way to try and fix this issue. And so I'm going to talk about 3 different sort of mini projects that we have on the go that complement a lot of our industrial work on degradation, frustration, and collection as sort of 3 themes. So if you do want to get a hold of me afterwards, you can look us up on Twitter. That's our Green Mat Lab Twitter account, or just send me an email, and happy to answer those questions for those of you who might be too shy to type your questions into a chat box. So I'm going to start with why. So you know, I think it's always useful to know from academics why they're doing what they're doing. Why are we so obsessed with trying to save the world? Well, a lot of this is because if you go and you look at the media in terms of what's going on, well, you quickly understand that it's all your fault, right? So plastics are evil materials. We should do away with them. Let's all pilot zero plastic households, and you know the problem will be solved. So it's down to the choices that we as individuals make. And when I have the privilege of interacting with humans in person, I often will say, okay, what would you do to save the world? Would you use the styrofoam cup to drink your beverage? I'll drink it in a glass right now. Or would you use this ceramic mug? And invariably, everybody goes for the ceramic mug, but I always raise my hand for the styrofoam cup. And the reason I do that is because I can make, transport, use, and dispose of 500 styrofoam cups for the total energetic cost of 1 ceramic mug. So we think about that context of plastics being evil. We need to think of it in terms of energy. We need to think of it in terms of carbon. And if I look at the footprint of that styrofoam cup, it's exceptionally lightweight. It's a waste, it's derived from a waste product from our fuel industry. It's easy to make, it's easy to transport. Great. If I look at that ceramic mug, I have an energetic cost to dig it up. I have an energetic cost of firing up a kiln to high temperatures to make that material. I have an energetic cost of transporting that heavy mug to bp-ICAM, I guess you're a Waitrose crowd, and then you've got to take that home as well. And so I look at that total use, and you would say, well, what you're not considering is the waste. And if you think about that waste at end of life, right? Well, the styrofoam cup you're going to dispose of, and then the ceramic mug you would reuse, right? And this reuse, if you use it more than 500 times, then the world is going to be saved. But the issue is whether or not you want to clean it, right? Because if you use hot water and you use detergent, well, you've got to make the detergent and take the detergent out of the water, and you've got to heat the water up. And that's the energetic cost of 2 styrofoam cups. And so the only way to do this in a sustainable way is a professorial way, right? And so if you've been in a professor's office, you realize there's a mug there, and that mug is encrusted with some sort of a black goo, and that black goo is because they drank coffee out of it and have never, ever cleaned it. And by the way, we all left those mugs in our office when we left. They're still there, and I have no idea what the state of our offices are going to be when we're allowed to return. So what do we do when we think about that grander challenge? Well, we can think about this idea of energetically comparing plastics to other materials in lots of different contexts. So packaging waste would quadruple in both volume and mass if we do away with plastics. Food spoilage will double because we have an exceptional barrier performance to many of these plastic materials. Vehicles are heavier, so our petrol costs increase. And we have no modern insulation, and so energy costs in terms of heating and cooling our homes would also increase. And so if I look at this, it's about 583 million gigajoules of energy per year. And I think even the BP people would probably not really understand that as a number. But if I want to convert that into something that BP would be able to understand, and a barrel of oil, it's about 100 million barrels of oil that are saved by using plastics each year. So it's a significant amount of energy, and therefore a significant amount of carbon that we're saving by using plastics. And so this changes the narrative significantly. Instead of saying, oh, okay, we should do away with plastics, it's not about that at all. We must use plastics, and arguably we should be using more of them. But the thing that we are not doing, and we must do urgently, is to have progeny over that waste and to have control over the fate of those materials. So we have to dissociate use and fate and do a dramatic job of recovering value from these materials that we use. So if I wanted to think of that as CO2, and I were to say, okay, well, what's Greater Manchester's target, right? Here we are sitting in Greater Manchester. We've got an aggressive target for our wonderful city. And this would be able to meet, the global plastics industry would be able to meet this target easily in a single year. This is a mammoth amount of CO2 that we can transform. So this is the challenge, is we have a plastic material which we as material scientists might know and might love, and then we have a public which really doesn't necessarily understand things. So they're going to focus on visible plastics, but they don't really understand the complexity of this. So I like to go out and talk to people who might not necessarily realize some of the nuance in this area. And one of these groups that I did talk to is Extinction Rebellion. And you talk to Extinction Rebellion, they're all about this carbon question. So we've got to solve this carbon issue in order to save the world. And that is urgent. But what they don't understand when you try and overlay those plastic numbers is that you have polymers or plastics in textiles, in face shields, including the PPE we use, in our shoes, in our electronics, and even in the adhesive that this guy is using to adhere himself to the wall of the London Stock Exchange. Boy, oh boy, this is a complex set of materials, each of which have a different potential fate, and each of which have a different optimal fate. So if I go and I talk to the general public and I say, well, what do you actually think is plastic? Invariably, they turn to the grocery store. And food packaging is a major, major player, especially because we have done a really poor job of capturing value from these materials. Why do we have them there? Well, actually, we have them there for really good reasons. They have dramatically improved food safety standards, and they have extended shelf life. And so they've minimized food waste, which is a dramatic reduction in terms of our carbon footprint. So people don't die and we save on carbon. Great, keep doing it. Well, why do we have, let's say, a black plastic package? Well, we have a black plastic package because the meat looks sexier when I put it on black. And so the marketing people can sell that piece of meat for more money than if they had it on a white package. However, there's a consequence here because the black plastic package is much more difficult to recycle than the white plastic package. And if I have comparative materials and one is recyclable, it has a much better end of life fate. One is not recyclable, now I've got a real problem. And if you have to make that choice and someone has to sort it, then oftentimes what happens is nothing gets recycled. And so if a decision about our plastics use isn't actually providing a benefit, we should do away with it, get rid of that, not have that plastic. But we must retain the plastics that are actually really important. The second thing to realize is that, well, to the general public, this is a plastic package, right? But for us as polymer chemists, it's not just one thing. We've got a plastic tray. We have a lamellar film that is probably 5 layers of plastic, each with a different function. We have adhesives and heat seals. We have a plastic reinforced paper label. Everybody thinks that paper doesn't have plastic, but it's got a lot in it in many applications. And then underneath the meat, we've got an adsorbent plastic mesh that's been soaked through with meat juice. And so again, not only do we need to understand the material, we need to understand how the society that's interacting with the material is going to feel about it. Because if I say, okay, can you please rinse this item and put it into your recycle bin? People might do that with the film. They'll certainly do that with the tray. And there's not a chance in hell that they're ever going to do that with a meat-soaked adsorbent plastic mesh, right? So we have to design materials and design systems that are driven by societal practice and not just by wishful thinking. Of course, we're now in a pandemic. Well, our complexity in terms of our plastic world has just increased. We've seen dramatic increases in terms of both the volume and the diversity of plastics that are cycling through households. But these plastics are, again, there for really good reasons. They prevent infection, they increase consistency in our hospital environments, and they improve sterility. We've got to keep doing those things. Those are important. Do we need to have people disposing of PPE on the streets? Absolutely not. Do we need to have excesses in surgical kits? Do we need to have disposable cups in hospital convenience spaces and cafeterias? No. So again, you do that same prioritization, or we're working with the NHS to do that right now, to be able to try and minimize their plastic and increase their plastic flow, increase the plastic circular flows. And then we have lots of products that I'm like, why do these things exist? If you ever want to get me raging about something, have a conversation with me about Christmas crackers over a pint, and you will see the rage boil over. But the one I wanted to talk about today was wet wipes, right? We used to be able to like go to the lavatory and clean ourselves and all was fine. Wet wipes are this new invention where we're sort of having these constant disposable items that are extremely convenient but questionable in their necessity. But what I wanted to talk about beyond wet wipes in general is this idea of advertising. Because this particular brand says that they have wipes that are 100% biodegradable and are 0% plastic, right? So if you think about plastic as a deformable material, that scientific term plastic, well, this is about 50% plastic, right? It's just not plastic that's derived from petroleum. And in terms of biodegradation, well, it does meet the EU criteria associated with biodegradation. If you were to look in the environment of release, which is either a landfill, if you put it in the right location, which is in your waste bin, or if you decide to flush down the toilet and that ends up in the sewer system, neither of those environments is this biodegradable. We see in our labs biodegradation of around 15% in materials like these. So this is a big problem because we don't have the same consistency or expectation in advertising. So what does a sustainable material look like? If we are going to try and design something, what do we need to consider to actually be able to do something that is smart? Well, the first thing is we have to recognize that polymers hold massive societal value. And so this is not a question where we have alternative things that are available. And many of the alternatives, such as, okay, we're going to switch to a biopolymer. This is still fundamentally a plastic that we have to have control over at end of life. Most alternatives that are on the market right now will produce more waste and more CO2. This is not to say that we don't want to invent in this area. It's not to stifle innovation, but it shows that there's a real danger here in terms of just saying, okay, we're going to go and switch things over. The second thing is that plastics are very diverse. And we've got to think about the end of life and optimizing that and removing that from systems where we can. And that means we've got to be able to identify and prioritize different pathways. So we need to identify whether or not reuse is good to do for a material, recycling, and that can be mechanical recycling or chemical recycling, degradation, biodegradation, or another form of degradation. And if we can't do those things, then a non-selective pyrolytic method is a good way to recover value, right? And so this is using these waste materials as a feedstock instead of going after petroleum sources. So an interesting pathway there, but there's an interesting one that's not there, right? And that's landfill. Really what this should be focused on is a systemic solution that avoids the release of plastic into the natural environment, because that is where there is a consequence for these materials. So zero plastic release is something really we should be getting behind instead of zero plastic. So what if we have a plastics-free world? Well, there's real consequences there. But if we have a world that recovers value from all plastics, we get to this state of no release. That's a sustainable system. So instead of thinking of this as a sustainable plastic, we want to be targeting sustainable systems to understand, in each case, the fate of this material in the environment. And the last thing I sort of want to harp on about, because I know I've been preaching for the last wee while, is that we have to get used to using past tense terminology. It does not matter if something is recyclable or compostable or biodegradable. It only matters if it is recycled, composted, or biodegraded. And so if we design something that has a particular purpose, but if that material is ending up in a landfill, or worse yet, ending up in our oceans, we have done nothing to change the fate of that material or improve its sustainability. So part two, what do we do? How is our sort of role as myself as a traditionally trained chemist, now a material scientist, what do we actually do in this space? Well, it didn't really start by working in sustainability and polymers. Started very much as an inorganic chemist designing catalysts. A lot of our early work was moving away from heavy metal catalysis and moving into earth abundant or benign catalysts. This is an example of an early vanadium work that we did. We also spent a lot of time thinking about topology control. Did a lot of work with polymer stars that are biodegradable as a way to control function in these systems. And again, started doing this work with industry. So we had designed, in this case, an iron catalyst. And we were really proud that this was an iron catalyst, but when we talked to industry, they didn't give a crap that it was iron. They did not care. But when we showed them how easy it was to decolor it, right? So we've got this very strongly colored catalyst, very easy to make a white polymer. Suddenly they were excited. And so by talking to industry early, we were able to try and design systems that were fit to their needs instead of being cute and thinking that we knew what was going on. That's, of course, underpinned by a lot of understanding. And so we feel that design is tied to understanding. And so we do a lot of mechanistic work. This is diagnostic stuff like I'm showing here, as well as a lot of reaction kinetics, which is a bread and butter of our group. That also allows us to be quite translational. So if we understand something, we can work with chemists across the spectrum and try and do something new. So this is a collaboration with Steve Thomas, who was up at the University of Edinburgh. We were able to take a catalyst, which was traditionally only used as a polymerization catalyst, and actually affect quite complex and difficult reactions like formal hydroaminations or aniline production in a really simple and atom economic and green way. We do applied work as well in terms of our collaborative research. So from the biomedical side, I'm not going to talk about this today, but we had work looking at oligonucleotide cross-linked hydrogels, which could detect with very good specificity microRNA sequences down to 10 picomolar levels. We did work on understanding the mechanism of titanium-based group transfer polymerization systems. Worked on very complex sugar mimics. So I had what we call a PEGOS. system was a synthetic amylose mimic, as well as more modern work on trimetallic zinc catalysts and projects that we're now doing, which are much more applied. And so we have all these work projects now in the James Lighthill building at the University of Manchester looking at extrusion, as well as water purification projects and projects on glass fiber insulation. So that gives you a bit of a flavor in terms of how diverse our group is, from the very fundamental inorganic catalytic stuff to, oh, okay, we're going to make some stuff that hopefully will go into your roof someday. But today what I wanted to do is to do a deeper dive into 3 specific areas that this group works on that I think showcase what sustainability means. So the first story I'm going to work from right to left is on a biodegradable polymer system that we've designed that really is quite interesting. It's quite different than other people have done before, but looks sustainable on the tin, and you've got questions about it. The second is a project that looks very unsustainable, but actually is inspiring a lot of work, which really shows the diversity of sustainability and what that means. And the third photo project is a project that is showcasing how important it is to be interdisciplinary in this space. And it's a project that we call one bin to rule them all, hence the joke with Frodo and his green bin. So for this first project, this is a bit chemistry. So for those of you who aren't chemists in the audience, hopefully you can follow along a little bit. But if I wanted to make a biodegradable polymer, those are often polyesters or polycarbonates. And from the polyester perspective, I can do this in a bunch of different ways. So I would be able to, say, take an alpha hydroxy acid and do a condensation reaction to make a variety of different polymers. And this is nice because these alpha hydroxy acids are readily available. Like I have a bunch of different R groups there. But it's an uncontrolled polymerization, so I only get very, very short chains, maybe a degree of polymerization of 5 at most. The best way to do it, the sort of most commercially relevant way to do this, is to take the diester. So some of you might be familiar with the monomer lactide or glycolide. And so you can do a co-polymerization of that or homopolymerizations to make polylactic acid, for instance. And this is probably one of the most commercially relevant biodegradable polymers, massive market influence for biodegradable polymers. But the difficulty here is that if I wanted to switch this to a different R group, so I wanted to target something like polymandelic acid, this is really challenging because I need to make this monomer. And that monomer is actually very difficult to prepare and is only available synthetically in about 5% yield. So to solve this issue, people have developed what are called O-carboxyanhydrides. And these carboxyanhydrides, we now can introduce lots of different R groups here. This is easy. And I eliminate CO2 as a small molecule in order to be able to drive the polymerization forward. Oops. And so what's great about this is its flexibility, but there's a major issue in terms of the synthesis of this requires phosgene gas or diphosgene. And so if you're going to go to industry and say, oh, okay, I've got this brand new sustainable polymer and I want to use a weapon of war as a synthetic intermediate in that system, there's always going to be issues raised. So it's very difficult to scale this up. And so what we did is we thought, well, if we can develop a system where we do this same elimination reaction, but instead of eliminating CO2, we eliminate a molecule that's perhaps easier to get the monomer synthesis to work, we might have something we can do. And so this is the basis of this project. We take an alpha hydroxy acid, we couple that to acetone or formaldehyde. I'm mostly going to talk about the formaldehyde work today, and make these dioxylane monomers. We can then do a ring opening elimination polymerization of that with a bunch of catalysts. Traditionally, we're using aluminium-based catalysts here to facilitate the reaction to make our desired polyesters. Monomers are actually really easy to do. So we do some scale up in our lab, up to 5-liter syntheses. So we can make quite a lot of this material for an academic group, I guess. And one of the important things to realize out of this is that our starting alpha hydroxy acid, we're going to have some chirality here at one of these sites. And whatever chirality I start with, I retain. And so I have retention of whatever enantiomer I use. So if I want to get the racemic mixture, or either the R or S variant of these, I can do this in very high isolated yields. And so I'm going to focus a bit on these mandelic acid derivatives because this is our first commercial target. Polymerization also works really well. The one here is, again, this aluminium-based catalyst. So we use a lot of metal-based catalysts, but they're usually earth abundant and very benign. And again, what I have here is a retention of whatever that starting chirality is. And because I'm doing a polymerization now, I now can make an atactic or an isotactic polymer directly from the monomer system. This is temperature controlled, so I need to keep my temperature below 130 degrees to prevent epimerization. And it's one of the reasons why we focus on the formaldehyde system, is because the polymerization is easier at those lower temperatures in the system. So I mentioned before that we do a lot of catalytic mechanistic work. So these aluminium-based systems, if we start down at the bottom here, I take my monomer, I do a coordination of that, and I'm starting from an aluminium alkoxide, and I basically have a tack at that ring. Acyl bond cleavage, which is the cornerstone of ring opening polymerization, however, is more complicated here. Because I have an ester acetal, I end up with this really unique functionality here. And if before I have elimination of formaldehyde, I have another equivalent of formaldehyde come in, this attack on the aluminium sort of instigates a Tushenko reaction. The Tushenko reaction, if you guys haven't sort of studied your named reactions in organic synthesis, oh my gosh, I became an inorganic chemist and then a polymer chemist to avoid named reactions. And now I'm stuck saying Tushenko every time. But what that does do is it gives me a formate chain end and a new methanol group. And so what this is doing is switching a living polymerization to an immortal polymerization and lowering my molecular weights. Because anytime I have a new chain end, I effectively cut my molecular weight in half. So think of it like this. If I have 100 monomer units, I would have a degree of polymerization of 100 there. But if I have one single Tushenko reaction happen, my degree of polymerization is now 50. If I have two happen, it's now 25. And that's a real problem in terms of controlling molecular weight in these systems. So how do we solve this? Well, one of the things we do is do a lot of work on catalyst design. And I'm not showing you our stuff on organocatalysts, but on this polymerization system, if I simply switch from catalyst 1, which is a very traditional catalyst in ring opening polymerization, for one which is slightly less controlled but much faster, I now dramatically increase propagation rates as well as not changing the rate of my Tushenko reaction. So competitively, I'm getting more polymerization versus Tushenko. The other thing I do is I switch to a dynamic vacuum-based system, and I remove the formaldehyde as fast as I can. Fortunately, we're not able to trap that out through other means. Vacuum has been the best in terms of our hands. And so if I just look at these systems with those conditions, I now can get up to 25.5 kilograms per mole, right, which is near where our target needed to be for our industrial partners. We have a partner in the United States that has now done this at scale and gotten 45 kilograms per mole, giving us a polystyrene mimic. And so the reason we started with this polymandylic acid is we wanted to get up to high glass transition temperature species so we could potentially replace polystyrene in packaging applications. And that gives us a glass transition temperature of about 110 degrees, which is perfect for the space that we're working in. So takeaways from this, we've got no racemization. So we have this lack of epimerization at 110 degrees, which is our polymerization temperature. That 25.5 gives us a TG of 98. And so we've been able to have this molecular weight correlation in terms of TG. When we do the polymerization, there was some people who were concerned about formaldehyde. Well, when I form that polymer, the paraformaldehyde exists as a sort of crust at the top layer of our reaction vessel. We can simply scrape it out, put it into a new monomer synthesis, and are ready to go. And it's interesting because you'd think, well, there'd be a little bit of formaldehyde left in the product, but any formaldehyde that is left behind actually gets incorporated in this Tushenko reaction to change our end groups. So we have no free formaldehyde in the product. And so the goal of trying to be able to produce this in a much less expensive way is realized. So we've had about a 250 times less expensive system to do than other methods. And this is without any savings costs from scale up. So it looks really good, right? Bit of other stuff to take you through some of the more modern stuff that we're doing. We have a strong interest in sort of exploiting this on other systems. So we can perhaps introduce cyclic rings in those. So we have a strong interest in using those to control crystallinity and control packing in these polymer-based systems. This becomes a lot less sustainable because our monomer route is much more difficult. But as a proof of concept, we wanted to show that this would work. So it's quite complicated to simply get to this derivative. We have worked with the other derivative before, but the trans derivative is the one that actually ring opens. So we have a selectivity in terms of the control from a tacticity perspective, simply by the energetics of the actual ring opening step. And interestingly, we see very different behavior if we think of this as a homopolymer candidate versus a copolymer candidate. So for homopolymers, we have to use quite an aggressive catalyst with diethyl zinc or other zinc salts to be able to facilitate this. We see no polymerization with our traditional aluminum saline system. But interestingly, we do get incorporation and in fact, an increase in speed of those reactions when we do a copolymerization. And so this is again showing the importance of understanding the kinetics of these reactions, as this is all down to reactivity ratios between our two monomers. We also do other applications in terms of our old biomedical collaborations. So this one on the left is a collaboration with Alison Hume, where we looked at appending alkynes using our DOX-based system into the framework. And these alkynes are much stronger reporters for Raman spectroscopy. And because there's a cell-silent region to Raman spectroscopy, you can actually visualize inside cells. The top line here is the traditional deuterium-based system, whereas the bottom line shows how much stronger a signal we get from the alkyne-based systems that we've designed. And finally, I want to come back to this idea of sustainability, right? So I've been harping on about how, oh, look at us, we can make polymandelic acid. We wanted to make sure that that was a good thing to do. And so we wanted to compare this phenyl DOX system that we have to make polymandelic acid to the traditional or best practice phenyl OCA-based system. And so if I wanted to look at that and make polymandelic acid, I can do an LCA with our collaborators, and this is Adisa Azopagic, it's in Manchester, and see what a good drop-off we have, 20.5 kilograms of CO2 per kilogram down to 14.2. So a big savings there. And we can see that the bulk of this cost is the mandelic acid that we're having to contribute to the system. But what's really important here is that you really understand how that works in the system, because we're not really looking to try and replace the existing PMA synthesis. We're trying to look to change polystyrene. And I'm like, wow, we are actually really bad. This is, unless we solve the problem with the mandelic acid synthesis, actually contributing to the carbon problem, not trying to fix it at all. So just something looks sustainable doesn't mean that it is. And so we're working with MIB now in Manchester to try and get much better routes to our mandelic acid that are more sustainable, which really will require us to couple those biological processes to renewable energy systems. So does this mean we're scuppered, we shouldn't do anything? Well, it's really important that what it does is it guides where we have an application space. So we have 3 different projects, 3 different industrial applications for this, and each of them are pointed at an area where you cannot recover and cannot recycle those materials. And so there is no alternative end of life, and you need to then facilitate biodegradation for very different reasons. So adhesives, formulation polymers, and cross-link systems are really big growth areas for us, and certainly areas where we'd explore collaborations with potentially some of the people on this call. So that's the first story and the longest story for those of you who are worried about what time it is. The next 2 stories are a bit shorter, but show, again, the diversity that our group works in. So the first is really inspired by someone challenging me to stop working with industry, and it didn't really work. So an old line manager I had at the University of Edinburgh said to me, oh, you seem to work a lot with industry. And we thought about doing something, interesting, implying that working with industry wasn't. I would question that. I think that we've had lots of fascinating conversations and some of the best projects we've ever done by working directly with industrial challenges. But this did inspire us to think about some of the work that we used to do in the past. So frustrated Lewis pairs. Well, a frustrated Lewis pair is basically an extension of a Lewis pair adduct. And so if I add a bunch of steric bulk onto a Lewis acidic species that's an electron pair acceptor and a Lewis basic species that's an electron pair donor, those 2 can't interact with each other. And so there's some latent reactivity here which can be exploited. And that's been done in small molecule chemistry by Doug Steffen and the people that were inspired by him. So you can do metal-free hydrogenation reactions. You can activate really weird small molecules lots of different interesting stuff. And what we wanted to do was to say, well, what happens when we extend this to polymer chemistry? So can we prepare a Lewis acidic polymer and a Lewis basic polymer that would then not interact with each other in the solution state at all, or in fact at surfaces? And then when we put a small molecule in, we get some sort of a response. So the concept is we take a designer boron and a designer phosphorus-based polymer, do copolymerizations with styrene or methyl methacrylate, traditional radical polymerization to make these polymeric frustrated Lewis pairs, and then induce cross-linking or gelation to be able to affect a chain. So hopefully this video is playing for you guys. It is for me. So if I take those two things and they're in solution, nothing is going on. I've got no change. I add my diethyl azo dicarboxylate, which is just a surrogate small molecule we're adding in because it gives us good reactivity. And almost immediately I have a transformation. And this sets very, very quickly just with that small molecule addition. In about 10 seconds, you can turn this over, but Meng, the PhD student and now postdoc who's working on this project, is taking his time to put the syringe waste safely, and he'll come back in and flip that vial over in a second. You can see from the figure on the left that this changes over time. So I start with a kinetically trapped gel, and I get a rearrangement here that then pushes out some of the liquid and gives me a thermodynamically set gel that's much tighter and holds less liquid in it. So what this means is that this is dynamic, it's changing over time, and it does mean that these are self-healing materials. If I have a very dried down system, the chains don't have a lot of mobility, and so I have to add solvent and take a while to be able to rectify this. But if I have a wet system, one that's retained a bit of solvent in there, I can either squeeze it together or put pressure on it from a rheometer plate, or indeed add a little bit of solvent to get that interface functioning well, and within seconds have a fully healed system. So dramatically fast self-healing that's allowed to take place. I also have a thermodynamically responsive system. So if I heat this up, I can break these crosslinks and revert back to my original form. And pleasingly, this happens at a relatively low temperature. And that's going to become important when we think about some of our future applications. For those of you who like rheology, I'll just sort of skim through this quickly, but I'm not going to go into it in terms of detail. Important takeaways are in the top left here. You can see that we don't have full recovery. And this is because we do have a Lewis acidic species that is quite sensitive. It's a very reactive system. And so because I have that in there, when I break those crosslinks and then I try to reform them, when they're broken, there's a brief period of time where those are sensitive to water or oxygen. And so we have a slow reduction in terms of the number of crosslinks we get over time. From these other systems, we can see that we have a Maxwell-like behavior observed. The time temperature superposition suggests these are acting as supramolecular gels. And I can change the flexibility of a system by changing my co-monomer. So I get a very different performance based on MMA than I do for having styrene as a co-monomer. So what are we doing now? Well, this is being recorded and is going to end up on YouTube, so I can't really tell you anything that's secret, but we've totally moved away from the original polymers that we've worked with. Our new system is much easier to make, it's easier to scale up, and it shows a much broader range of chemistry that we can work with. So the three application areas that we're looking at is sensing, so we want to be able to sense different substrates. The substrates that are used in the vials that you see at the top here differ by as little as a single carbon, and you can see the dramatic changes both in gel strength and color that we're observing in these systems. We also have other substrates that are introducing viscoelastic behavior and work as triggerable adhesives, so there's no adhesive behavior until you have that switch, and then a single molecule introduces that adhesive performance. And the final one is looking at catalysis. And I thought about how much I could tell you about this, but I really can't tell you anything. So it's catalysis. It's very interesting and is supremely sustainable. So what we want to do is we want to exploit what looks like a really unsustainable polymer, but because we're able to affect these transformations, we think we're going to be able to make some real dramatic changes to the sustainability of these systems. The third story, just as I come to a close here, is to come back to Frodo and to come back to those original challenges. Because what I have here are two very technocentric solutions, right? I might be able to design something, but I haven't talked at all about the system of provision, the system in which these would exist. And I want to really highlight the whole reason I sort of came to Manchester in the first place. And it's not that Bill Sampson wasn't a nice guy or that the materials department wasn't world leading. It certainly is, but I was really attracted by the power of the Henry Royce Institute. And so we can sort of lead on sustainable materials within HRI and then accomplish tasks to do with synthesis, but really extend ourselves and think about a hierarchy of materials. And that means we get to get involved in conversations around waste management and material valorization, and actually start to look at those challenges around the wet wipes, right, where we have tests which really do not test for biodegradation, and try and explore new methodologies to develop tools to accurately represent biodegradation and composting, as well as improve our understanding of recycler quality and mechanical recycling. To do this, we've secured funds from the European Structural and Investments Fund to launch the Sustainable Materials Innovation Hub. This is hopefully, once COVID allows us to build things and be in things, will be the best facility in the UK to explore these things. And in the same lab, we're going to be able to make things. So this top bit of the lab is for synthesis, analyze things from the thermal, the permeability, to the mechanical characterization, to actually look at these at end of life through biodegradation, through an industrial composter, and through extrusion. And so a powerful facility really focused on not just doing the innovation side of things, but on translating that innovation into SMEs which urgently need it. And the last thing I sort of wanted to do as a framing exercise to talk about how we build those things. Because if we're going to go and have those solutions, we need to be able to have a team that's not just material scientists, but material scientists, social scientists, economists, manufacturing experts. In our early years before the hub, we were doing this through a program called Rethinking Resources and Recycling, which was really a well-funded and dynamic organization that first had it as basis training to show us how we can actually work in an interdisciplinary way. And the one project that this enabled was the One Bin to Rule Them All project. And it was entirely driven by stakeholder interactions. And it took an imagined future where someone in their home, regardless of what they thought was plastic or how much scientific knowledge they had, anything they think is plastic, they can put into a bin. And it's our job, just as we have with wastewater treatment, to be able to make that safe and to retain value. And so we felt this was the best way to eliminate plastic release and get the quantities of recyclate that was going to be able to be developed into products. So how does this actually work? Well, if you imagine one bin, now not only do you have some plastic bottles in there, but you've got kids' toys and films and all kinds of different things. And so instead of saying, okay, we're going to sort, which we do now, based on is this polyethylene terephthalate or does this have an ester bond, we're sorting it based on an external or an internal marker. And that marker might be something embedded into the system, or it might be something printed on it in an invisible way. But we then decide what to do with that based on the progeny of that material. So where has it come from? What's it gone through? And so we can identify paths for reuse or paths for mechanical recycling. We can track how many times that has been recycled in order to optimize when we should switch to perhaps a chemical recycling pathway. And for chemical recycling, we can then look at strategies for doing selective or, in fact, general pyrolytic methods to minimize our influx of oil and then use this to improve the virgin feedstock that we use to develop new products. Selectivity, recyclate tipping points, and robust materials are the three active research areas that we have from a materials perspective. And this is complemented by Maria Sharmina's work on business models, working at the Tyndall Center, and Helen Holmes' work out of the Sustainable Consumption Institute that looks at social practice. And it's remarkable how quickly this has garnered a lot of attention from industry. So these original industry partners have actually been extended to an even larger community. And they go from small little SMEs up to some of the largest brands and largest waste management companies on earth. And so what have we learned from this already? Well, it's weird to go and give a materials talk or to a chemistry audience and talk about social realities, but so much of this is dependent upon this. And what someone does with their waste is very different if they're at work or if they're at home, if they're on a high street. Material realities is all tied to sort of our expertise. And it's really recognizing that different pathways might be available for even something that looks like exactly the same material. And all of this is underpinned by a knowledge of what's going to work for businesses across the supply chain. And what's interesting is that the solutions are not necessarily technocentric. It's about policy. We've got to have standardization. We've got to have policies that enable that standardization. It's about infrastructure investment and investing in the right infrastructure for the right purposes. It's about creating higher value recycling. Right now, we predominantly export our plastic waste because we don't have mechanisms in place to create value out of it here in the UK. And it's about shared business models and relationships that exist across the supply chain instead of just at one site. So that's it in terms of what I wanted to talk to you about today. We've got big challenges ahead of us in terms of sustainability and plastic recycling, but the who is really what matters, because we have perhaps a little bit of the David Attenborough effect happening in our group right now, where we have lots of people who are exceptionally passionate about this field. And I can get up and parrot on about why this is important, but the reality is all of our success is underpinned by the people who actually do things. So the people in red who are up at the top are the ones who I've talked about their work today. You can see the names of other people who have other really interesting projects that I either can't talk about because we're working with industry on them, or I just didn't have time to talk about the really cool stuff today. We've got a really strong alumni base who continues to be involved in our group that have gone on from anything to be patent lawyers to industry leaders to academics themselves. And we really lean on our collaborators. And this is especially true now that we've become much more interdisciplinary. And so just a shout out to Helen and Maria and Adisa here in Manchester for the work that they're doing to really help add value to the work that we're doing. Finally, thank the funders who are providing us with the resource we need to enact these changes. And I thank you for your attention.